So where we started with this idea of integration was finding the area of these irregular shapes. So we're going to have a look at it in a little bit more detail, because one of the things we said was if it's below the x-axis and we integrate, we actually get a negative answer. And obviously you can't have negative area. So how do we deal with this? So here's some random curve and there's a bit above and a bit below. Say I wanted to find that area from A to B. That's not a problem because it's all completely above. So that would just be the straight integral from A to B. Not a problem. But if I wanted to find this red area from B to C, it's underneath. So the actual integral is going to give me a negative answer. So to find the area, it would be the negative of the integral. So there's a number of ways of handling that. So if I want to find an area below the x-axis, yes, I could just say, all right, it's going to be the negative of the integral. Another way some people like to do it is they say, oh, well, it's the absolute value of the integral, because absolute value will always give me a positive number. And another way of doing it, remember I said we can swap the limits round, but we change the sign. And so if we swap the limits round, it then becomes a positive again. So let's have a look at this example. There's back to our cubic again, a little bit dodgily drawn, but anyway. And I'm going from -1 to 1. Now, because of symmetry, I know the actual integral, of course, would be 0, or it should be. So I need to break it up into its two parts. And I could say, well, okay, well, the bit that's underneath, I'll say the minus of that integral. And then the bit that's above would be plus that integral. That's one way I could deal with it. The integration, obviously, is the same for both of those. And then we sub in and we come up with our answer. Of course, there are other ways we could handle that. Because of the symmetry, I could, of course, say, just like we do with an even function, if I want to find the area as opposed to the integral, I could say twice the integral from 0 to 1. So using the symmetry, I could go twice the integral from 0 to 1, and then I've only got one thing to substitute here, I suppose, less numbers to play around with, and we obviously get the same answer. So if it is an odd function, that's one way of handling bits underneath. We can use the symmetry and just go twice. But again, it has to be symmetric. So here's, another cubic, a bit above, a bit below. Not sure, to be honest, whether those areas are going to be identical. Depends on the equation, I suppose. It's the area from -2 to 1 would be positive. And the area from -1 to 0, well, that's negative because it's below the axis. Notice I've changed it to plus, but I've swapped the limits around. The advantage of doing that is, notice how now on both of these, -1's on the top. So I don't have to substitute in -1 twice. I can simply say it's twice what I get when I substitute in -1. So it gives us one less substitution, I suppose. So when I do this one, I can go, okay, twice what I get when I sub in -1, because remember it's plus the top limits, and then it's minus the bottom limits. So minus what I get when I sub in -2, and minus what I get when I sub in 0, well, that's just 0. And that also, by an amazing coincidence, is a half. That was our answer to the last example too, wasn't it? Not everyone will come out to be a half, okay? Just a coincidence, just a coincidence. What happens if the area is going to the y-axis? Well, it's exactly the same, but now we need to do everything in terms of y. Okay. We'll need to rearrange y, because we need to make x the subject. So I've got some function of y instead of some function of x. So the first thing I do is make x the subject. So I get some new function there, g of y, whatever that turned out to be. Then it'll be the y coordinates we substitute in instead of the x coordinates, because we're going from along the y-axis. But then our integral is basically the same thing, but now it's with respect to y instead of with respect to x. So here's our, it looks like a parabola. That's because I've cheated with the shape for drawing purposes, but I've called it x to the power of 4. Remember, of course, it actually would be flatter at the bottom and steeper at the sides. We're going from x values of 1 to 2, but we want the area to the y-axis, not the area to the x-axis. So first of all, rearranging that, making x the subject, that'll become y to the power of a quarter. And I'll be integrating from the y values. So 1, well, it's still 1. But when we sub 2 into that equation, we get 16 for the y value. So add 1 to the power over the power, sub in 16, minus sub in 1, and we come up with our answer. Here's the interesting one. What happens if I want to find an area that's trapped between two different curves? So here's one curve, function x we'll call it. Here's another curve, g of x. And I want to find that area that's trapped between the two curves. How do we deal with this? Well, the first thing I'm going to need are the points of intersection, because that'll tell me where we're integrating from. So we'd solve the curves simultaneously and come up with our answer. Now, clearly, the area I'm looking for is the area under the red curve, take away the area under the blue curve. So I guess the biggest thing is to make sure you know which curve is on top. And so for those lazy people amongst us who hate drawing pictures, you're going to go, oh, hang on, which one's on top? That's why diagrams help, so you know exactly which one's on top. And then it'll be the area under, well, that's integral of function x minus integral of g of x. But of course, because they're both going from a to b, I could combine that all into one integral. And it'll be whatever function x minus g of x. There might be some terms that end up cancelling and make the integration a bit easier by doing it that way. So we're going to look at x to the power of 5 and y equals x. There's y equals x. There's y equals x to the power of 5. So I only want the positive section. If it was both of them, again, I could use symmetry and say, well, it's twice that amount. Point of intersection, hopefully it's obvious, but in case it's not, we could solve them simultaneously. X to the power of 5 is equal to x, wonder what number? Oh, look, 1. There we go. So we'll integrate from 0 to 1. Now, the interesting thing here is, if you do end up solving simultaneously, the function you end up integrating actually is very similar to the equation you just solved. Well, of course it is, because that's exactly what you do. When you solve simultaneous equations, you subtract one from the other. And that's what we're doing with this area too. We're subtracting one function from the other. So x minus x to the power of 5, half x squared minus a 6, x to the 6. Subbing in, there's a third. Now, if you are lazy, of which one or two of you might be accused of that, and don't want to draw your diagrams, and you get it the wrong way round, what's going to happen? Yeah, the answer is going to come out to be negative. So you know, oh, got my functions the wrong way around. There is a long way of fixing that, and there's a quick way of fixing that. That's the quick way. Right? The long way, of course, is to rewrite the whole thing out. The quick way is to chuck absolute value signs around everything. Then it becomes positive. Right? A better way is to draw the diagram in the first place, and then you don't have the issue. Here's a 2002 question, where in this case it's all below. Y equals x minus 4, x squared, and they've even helped us out by giving us the point of intersection there, 4 naught, and the other one is A. Find the coordinates of A for 2 marks. Oh, multiply together, give 4. And of course, they've already given us one answer, so we knew that it had to factorise to be x minus 4 anyway. So the other one is x minus 1, so that must be where x equals 1. So the coordinates of A, 1, and then when we sub it back in, we get negative 3. Now go and find that shaded area. Okay, well, the line is on top. So it'll be x minus 4 minus the parabola, x squared minus 4x, and we're going from 1 to 4. Now, something interesting will happen here when you see the answer. Because remember, this area we're looking at is below the x-axis. So I'm expecting a negative number. Because we said if the area is below, it's going to be negative. Well, let's sub into our integration. Oh, it's positive. See, the thing is, when you're dealing between areas between two curves, you don't have to worry about what's above and what's below. Okay? It will always, as long as you put the top one minus the bottom one, it'll always come out to be positive. The reason being is this. The one we just did, it was all below. Okay? So let's say we said, okay, it was function x minus g of x, and that was all below. But I could get that picture, shift everything up, oh, who cares, 1,000,000. The area is not going to change. But now I'm going to say it's the curve function x plus 1,000,000 minus g of x plus 1,000,000. Whatever I've just added onto them will cancel. And I'll still get function x minus g of x. Yet now it's all above. And so that's why it doesn't matter. Okay? That's why it doesn't matter. It does with the other ones because we're only talking about one curve with the other ones. And obviously if I lift one curve up, I'm going to change the size of the area because we'll automatically be going down to the axis. But when we're just dealing with the boundaries of two different curves, not a problem. It'll always come out to be, again, assuming you put the right one on top, it'll always turn out to be a positive number. So here's one here. That's quite a difficult one. That's why it's question 8, actually. Well, 4-2 in it. In that here's the area, and they've left a little bit out underneath here and so on. So the shaded region, we've got the circle radius 2 and a parabola there. And the x-axis. They've given them a hint by saying, by considering the difference of two areas, find the area of the shaded region. There's the hint. Which two areas are they talking about? I wonder. Okay. Well, we could break it up, I suppose. Because there's different boundaries. See, remember, the difference between the two is top curve minus the bottom curve. Now, as soon as that changes, and you'll notice, if I start at the y-axis, it's the circle minus the parabola. Circle minus the parabola. But then I get to a point where it's no longer circle minus parabola. So it changes. That's where we have to split it up into two different areas and find them separately. Because the boundaries have changed, if you like. So I could draw in that red line there and say, all right, well, the first one's the area between the circle and the parabola. And the second one is between the circle and the x-axis. And then obviously I could add those areas together. But their hint doesn't say considering the sum of two areas. Let's have a look at it. Much more efficient to do it this way. Subtract that area under the parabola from the quadrant. You see, remember, integration is useful for finding the area of irregular shapes, things we don't have a formula for. But I do have the formula to find the area of a circle. So why on earth would I integrate when I've got a formula that does it a lot quicker? So I can say, well, the quarter of the circle is a quarter of pi r squared, and then I'm going to subtract the area under the parabola from 0 to 1. And that's what they were meaning in their hint when they're saying, oh, considering the difference of two different areas. So we can sub that into our integral. And there we go. Pi minus 5/6 units squared. So things like straight lines, if you were to integrate straight lines, when you think about it, you don't really need to. Because a straight line could end up being a trapezium or a triangle. You've got a formula for that. And that may well be quicker than integrating. Mind you, it's not that hard to integrate a straight line, I suppose. Okay. Playtime.